All right, in the previous lesson, I alluded to the fact that we don't only measure angles in degrees. Now, it's the most commonly measured in degrees. Math specifically is one of the few subject areas where we actually don't like degrees as much. Well, in geometry, we're okay with it, but when we start getting into trigonometry and building up towards calculus, we start liking the degree less and less. All right, so the question is, what is a degree? And it's funny because when I ask my students, what is a degree, it seems like a very basic question. We kind of joke what a silly question that is. But the fact of the matter is it's harder to um, describe than you would think. I mean, it's kind of like saying what is an inch. Well, it's a unit of measurement and measures an angle, right? A degree measures an angle, but how? How does it measure that angle? Well, we know that 90 degrees would be like a hard right. If I was facing north, 90 degrees turn, I'd either be facing east or west. If it's 180 degrees, I'd turn completely around. So I have to think in terms of a compass, right? So that's how many degrees is in each. So in terms of a compass, well, a full circle, a degree essentially boils down to the fact that it's 1/360th of a circle. Which begs the question, why 360? Why not 100? Why not 50? I mean, we're in a decimal system, 100 or 1,000. Why not? So usually in terms of measuring a circle or measuring an angle, we want something that's, when we divide a circle evenly, that the unit measurement comes out evenly as well. It's not in decimal or fractions. So you can think if I divided, if I had half of a circle or a third or a fourth or a fifth, well, we kind of like degrees because if I'm dividing it into these, well, sevenths doesn't work, but for most of these, you'll get a nice even degree measurement. All right, a half a circle is 180 degrees, right? 1/3 of a circle is 120 degrees. A fourth of a circle is 90 degrees. A fifth of a circle is 72 degrees. It's still a whole number. It's kind of an ugly number. Right, a sixth of a circle is 60 degrees. An eighth of a circle is 45 degrees. A ninth of a circle is 40 degrees. A tenth of a circle is 30 degrees. So I have heard some say because the Babylonians were on a hexamal system, which means they're base 6, that they liked 360, but it's not like 360 would be particularly useful in a hexamal system either. Um, I mean, I think in terms of a hexamal system, that would be something like 100 and, let's see, 140, right? If we were in hexamal, it would be 140. That's not a particularly nice number anyways. So don't really buy that. I do think it's because there's a lot of factors of 360, right? It's very easy to say if I had an eighth of a circle, I took a quarter turn, or all these degree measurements come out to whole numbers, right? If I took 1 times 2 times 3 times 4 times 5, that's 120. Times that by 3, that's 360. Even if I did times 6, I mean, 720 degrees would be nice. They picked 720. I don't know why they picked 360 instead of 720. Could have to do with the calendar year. A lot of times our calendar used to be based off of 360, not 365, right? And have a nice circular calendar. So a lot of different reasons why, but essentially a degree is a 360th of a circle. All right, so it is an arbitrary number, so we could say there's 100 Freds in a circle. So if we had 25 Freds, right? Well, if there's 100 Freds, that means 25 Freds would be a quarter of a circle, right? So if I times that by 360, well, that's the same thing as a quarter. A quarter of 360 is a 90-degree angle, so a 25 Fred angle, same thing as 90-degree angle. All right, if we do the reverse of that, so we have 100 degrees, right, which should only be a little bit more. All right, this is 90 degrees, so 100 degrees would be a little bit more. So we should expect it to be a little bit more than 25 Freds. All right, times that by 25. Okay, I can reduce this. Well, that'd be 10 over 36, which is the same thing as 5/18, right? That doesn't come out evenly, so we get 125 over 18 Freds. So that's 5 Freds, 6 Freds, almost 7 Freds. right? Um, oh, what am I doing multiplying by? I should multiply that by 100. It's taking 25 from the other problem, so times 100. All right, we get 500. All right, so 20, that'd be 360. 25 would be at 450. So 27, so it's about 27 Freds. It's a little 27 some change. I'm not going to tax myself too much in the mental math. All right, made that mistake earlier, putting 25 there instead of 100, but all right, so you can see I can convert between Freds and degrees just by proportional reason. Same thing if I had bobs, right? What is 30 bobs? Well, 64 bob, right? So 30, this would be 32 bobs, so maybe 30 bobs, something like this. So in degrees, expecting something close to 180 degrees. So I'd have 30 over 64 times 360. All right, well, 8 goes into both of these. 8 goes into 64 8 times, goes into 360 45 times. Then I could, have 30 over 8 times 45. 30 over 8 reduces to 15 over 4 times 45. So that's 675 over 4. So that goes in 150 times plus another 18. So it's about, let's see, 169 degrees. Just about. I think it's 168.75, but right, and we could reason it's going to be less than 180. All right, what is 45 degrees measured in bobs? I do know it's an eighth, but let's look at it. So 45 over 360 times 64. 45 actually goes into 360, so it'd be 1/8 times 64. So this is 8, be 8 bobs. All right, so what is the other measurement? It's actually called a radian, and a radian is actually defined in terms of a circle. It's not an arbitrary number. A radian talks about how many times, if I had the length of the radius, how many radius lengths would fit into the circle's circumference. All right, so if I took that length and I measured, and I was like, okay, that's one radius length or one radian, and then I took another, like that's my second radian or radius length, and then I took a third, and a fourth. My question is how many radius lengths would fit around the circle? Usually when I do this in class with students, we'll take a piece of string and you can make your circle with that piece of string and then use the same piece of string to measure around the circle. And depending on how accurate they are, I usually get that there's about 6 or 6.5 or 6.25, a certain amount of radius lengths. Well, if you go all the way back to circumference is equal to 2 pi times r, it'll fit into a little bit more than 6 because it fits in 2 pi times. So there's actually 2 pi radians in a circle, right? It's about 6.28 radius lengths would fit around a circle. So radians actually measured in terms of a circle. The big thing is that if we think of Freds as 100 Freds in a circle or 64 bobs or 360 degrees, for radians it's 2 pi. So what is a 180 degree angle measured in radians? Well, it'd be 180 over 360, right? Those are both in degrees, times, well, we want to know what is 2 pi. Well, 180 over 360 is half of a circle. So you do half of 2 pi, which is just pi. Pi is the same thing as 180 degrees. All right, it says what is 2 radians measured in degrees? Now, radians usually are in terms of pi because the circumference of a circle has that ratio of 2 pi. But if I was doing just 2 radians, it would be 2 times, all right, and I would need a conversion rate. So it would be 360 for every 2 pi. Those 2's would cancel out, and we'd get 360 divided by pi, which I think, right, pi is about 3, so that's about 120. Pi is a little bit more than 3, so I think it's something like 115 degrees. All right, but radians we usually don't measure them unless we're doing in terms of pi, because again, just like we're doing Freds and Bobs, we want it to be a nice even portion of a circle. So if a full circle is 2 pi, a lot of times when you're measuring radians, you're using it in terms of pi. And even when we start scaling graphs and graphing these in terms of radians, it's going to be in terms of pi. The reason that in math we prefer radians to degrees is that when we start analyzing these functions and we start having inputs, you wouldn't want to be doing a problem and all the inputs are real numbers, but then, oh, you're using a trig function and you have to use this mythical measurement of degrees. A radian's actually a real number. So you can use that as an input, just like you would input something into x squared or x cubed. So it's no different than any other real number, and that's why we prefer radians. All right. But before then, we need to practice converting between degrees and radians, and then we'll actually go back to the unit circle and look at, okay, what are all these special unit circle numbers, right? All these degrees that we particularly like, and what would they be in radians? Getting used to working with radians. All right, so maybe I say I have pi over 5 radians. What is that in terms of degrees? So there's always that conversion rate, right? We know a full circle is 360 degrees or 2 pi. Now the thing is when I'm using that conversion rate, well, 2 goes into both of those. So we think of in terms of half a circle, the conversion rate we're going to be using a lot, because we wouldn't like that since it always reduces. As a half a circle is just 180 degrees to pi, right? So if I wanted this to be in degrees, I would say times 180 over pi, right? Or 360 over 2 pi, right? This is essentially a tenth of a circle, right? These would cancel out, right? And then I would be doing 180 divided by 5, which is 36 degrees, right? And the reason I'm saying it's a tenth is, well, pi over 5 is the same thing as 2 pi divided by 10. So I can see that, oh, it's a full circle divided by 10, or 360 divided by 10. All right, what about 110 degrees? What would that be in terms of radians? Right, and I could take it as 110 over 360 times 2 pi, or I can just think of it as the conversion rate of pi to 180 degrees, right? These are going to come out the same. Those 2's would cancel out. I get, right? Some people like that proportional reasoning though. 110 over 360, right? That's a portion of the circle times 2 pi's. We're getting a portion of 2 pi. This works more in terms of dimensional analysis, kind of think of, oh, there's 12 inches in a foot. You always set up to 12 inches over a foot to convert, all right? The 10 factor of 10 would come out. All I'm left with is 11 pi over 18. I'm done. So in terms of radians, it'd be 11/18 pi, right? All right, so what if I have, I don't know, 57/6 pi? And I want that in terms of degrees. Now this is where that proportional reason, it's like 57 out of 6, but it's, we want it to be out of 2 pi. It doesn't really work well when we're starting with radians. It kind of works well with degrees, you know, any degrees that's between 0 and 360, you can go, oh, it's 200 out of 360. But I kind of prefer, you know, that dimensional analysis approach of going, all right, well, I want my pi's to cancel out. So this is in terms of, you know, this is radians, and I have pi radians, and I want to get to degrees, right? And there's 180 degrees to every 1 pi. Well, the radians cancel out, and then I'm just, right, pi's cancel out. 6 goes into 180 30 times. Then I just multiply. So that times 30, that's 570 times 3, which is equal to 1,710 degrees. All right, it's harder to use that proportional reason. We could also say, oh, you know, so I sometimes see students doing this where, well, every 2 pi is 360 degrees, so it's kind of like 12 over 6 plus 12 over 6 plus 12 over 6, 12 over 6. All right, we could break this thing apart. And then plus 9 over 6 pi. And they usually mess up somewhere. I've seen them use this reasoning, and it'd be a 360 plus 360 plus 360. A lot of times they just mess up, maybe they say they either double it or they half it. They might make this 180 instead of 360, or they might make it 6 over 6 and go, oh, 6 goes into 57 9 times, and then they do 9 times 360 instead of 9 times 180. And then I could break this into pies, that'd be 180, and then half of that, so 270. All right, that'd come out to 1710. All right, so some students like that kind of approach of, what if I do 57 divided by 6? And that comes out to 9.5. Well, if I do that 9.5, you gotta remember this is in terms of pi. Pi is 180, so you'd have to do 9.5 times 180, which is the same thing as 57 times 30, and come out to 1710. And so that's another way to do it, but that pretty much necessitates a calculator. So without a calculator, it's better to just reduce fractions. All right, what if we start with, I don't know, a large degree amount? I got 2,400 degrees. Well, I know I want my degrees to cancel. Or I can make it 360, or I can make it 180. And the reason I don't like 360, right, if I did 2 pi over 360, if I'm reducing fractions, I'm going to reduce this to pi over 180 every time, so I might as well just start with pi and 180. All right, then I'm looking for numbers that go into both of those. I can see a 10, all right, so maybe I make this 24 over 18, and now I can see a 6, all right, and that would be 4 over 3. Oh, just a 0. I say that seemed a little too small. All right, only one of the zeros would cancel out, right? It'd be 240 over 18, which would reduce to 40 over 3 pi. All right, I could also, again, try to divide, see how many times 180 goes into 2,400. It's easier just to reduce, so you're going to keep it in fraction form anyways with radians. All right, so you just want to know that conversion factor of 180 to pi. All right, that would be if I was starting in radians going to degrees, or pi over 180. And then you're just reducing fractions. All right, hopefully that made sense. It's okay if you make mistakes. Even I make mistakes, especially when we're doing this mental math. I mean, with the calculator, it's a little bit easier, but you do want to look and be able to recognize common factors. If you can't recognize common factors, you probably would want to take one of those approaches of, so if I went ahead, let's see if I can pull up a calculator real quick. Let's see. All right. So how could I do this with the calculator? If I'm a struggling math student, I'm not really good at dividing quickly or good with mental math. How could I do the same problem? Well, I would need to do 2,400 divided by 180. All right, and I get 13 and a third essentially. So it's like 13 and a third pi. Right. Because I would be times that by pi, so 13 and a third pi. You don't really do mixed numbers, so I do 13 times 3 is 39. 39 plus 1. So I can still get 40 over 3 pi. Still have to have some knowledge of fractions though, and if I couldn't get that fraction, now some of you guys have calculators where it'll just go to 40 over 3, and if it does, that's great. A fancier calculator, you could easily just go 2,400 divided by 180, gets you left that fraction. Let's look at one real quickly too. If I was starting in radians, just for an example. I don't know, 31 over 4 pi. So I usually think of a fraction that doesn't already divide evenly. All right, so times it by 180 over pi. All right, those cancel. And essentially I'm just doing 180 times 31 divided by 4, 1395. All right, without a calculator, you have to know common factors. Well, 4 goes into 180 45 times, and 31 times 45 is 1395. But you can see you can use a calculator to help you out. Really only need a 4 function one, but if you don't know your fractions that well, that's where you're going to be struggling without a calculator. Even with a calculator, you'll have to know, if I get this decimal, how do I make this decimal into a fraction? So hopefully this is helpful in terms of converting. The next thing we'll look at is on a unit circle, well, what would all those radian measurements be, and how can we quickly fill those in, as well as any tricks to quickly fill in any of the coordinates. All right, hope this helps.